Hello and welcome to this recording of Health Hazards Special Emphasis Program OPN 135. This course will give you an overview of the 5 items in the Health Emphasis Program that includes lead, hexavalent chromium or chrome-6, isocyanates, beryllium, and silica. Each one will be looked at individually. We will cover exposures, health effects, and abatement methods for each. So why a health hazards SCP? Well, in 2006, the North Carolina Department of Labor launched a health hazards special emphasis program for several chemicals that had serious health effects. Now, over the years, this has changed until our most current change, which is now including beryllium as a part of this SCP. Now, as a part of this emphasis program, OSHA's goals is to perform 200 inspections in industries that may use these chemicals. Now, as we go through this program, we're going to look at each of these chemicals as used in general industry and when they cross over into the construction standards. We'll also look at the description of each chemical, health effects, their permissible exposure limits, required medical surveillance, and some abatement procedures. The first chemical we're going to look at is lead. Lead. So lead exposure is a leading cause of workplace illness in both construction and general industries. Now, when someone references the lead standard, they're talking about metallic or inorganic lead. Lead can be used as a pure metal. It can be combined with another metal to form an alloy or in the form of a chemical compound. The primary use for lead in the United States is in automotive lead-acid storage batteries, which is a type of rechargeable electric battery. Now, lead alloys are typically found in ammunition, pipes, building materials, solder, radiation shielding, and even in fishing weights. Lead is also used as a stabilizer in plastics and also used in ceramic glazes. Now, exposure in the construction industries usually involves tasks such as welding, cutting, brazing, or blasting on lead-painted surfaces. A common exposure in general industry is at indoor and outdoor shooting ranges. So let's look at how lead can enter your body. In occupational exposures, lead is most commonly absorbed into the body by inhalation. When workers breathe in lead, it's as a dust, a fume, or a mist, and their lungs and upper respiratory tract absorb it into the body. Lead can also be absorbed through the digestive system if it enters the mouth and is ingested. A significant portion of the lead inhaled or ingested gets into your bloodstream. Once in the bloodstream, lead circulates throughout the body and is stored in various organs and body tissues. Some of this lead is filtered out of the body quickly and excreted, but some remains in the blood and tissues. As exposure continues, the amount stored will increase over time. The lead stored in the tissue can slowly cause irreversible damage, first to individual cells, then to organs, and then to whole body systems. Lead serves no useful purpose in the human body. Its presence in the body can lead to toxic effects, regardless of age, gender, or exposure pathway. Now let's look at how lead exposures actually affect the body. Now, intense short exposures to lead, these can lead to serious acute health effects. These symptoms can range from a metallic taste in the mouth, vomiting and diarrhea, to intoxication, coma, respiratory arrest, and even death. The symptoms observed in exposed employees will depend on their individual genetics and the level of the exposure. Now, high-level, short-term exposures that can cause serious health effects are fairly unusual, but they do happen. Please keep in mind that children are more susceptible to lead than adults. The acute effects listed here are typically found in children who have ingested lead. This is why it's so important to follow good housekeeping and good hygiene practices so that you don't track these substances like lead back home, where your children could become exposed. Now, the chronic health effects of lead, this occurs from lower level exposures, but continue for a much longer period of time than the acute effects we just looked at. The cumulative buildup and exposure to lead in employees' tissues can lead to a multitude of health issues. Common symptoms of significant long-term lead exposure can include loss of appetite, constipation, nausea, and stomach pain. Symptoms can sometimes manifest as excessive tiredness or weakness, weight loss, and insomnia and irritability. These are warning signs that something is wrong, but they're often misdiagnosed by physicians as something else because they're unfortunately common to a variety of health problems. Make sure you inform your doctor that you work with lead or are potentially exposed to lead to help ensure a proper medical diagnosis. Now, as exposures continue, workers can develop fine tremors and numbness in their extremities. And late signs of lead intoxication are slowed nerve conduction and forearm extensor weakness or wrist drop. These are typical signs in workers chronically exposed to high lead levels. Now, chronic exposure to lead that continues unchecked can lead to damage of the nervous, blood, urinary, and reproductive systems. There is also evidence that lead is a human carcinogen. Workers can develop stomach cancer and lung cancer following inhalation exposure. Further research is ongoing, but it's important to remember there's no safe exposure levels to carcinogens. Let's take a look at exposure limits. Now, the PEL, or the permissible exposure limit, that's the amount that the OSHA standards list as the legal limit, which cannot be exceeded. For lead, the PEL is 50 micrograms per cubic meter as an 8-hour time-weighted average. Now, the action level is when air concentrations of lead are high enough to trigger the initiation of required activities. Now, OSHA defines the action level for lead as employee exposure without regard to the use of respirators to an airborne concentration of 30 micrograms per cubic meter averaged over an 8-hour period. Now, at a minimum, when the action level is reached, the employer must initiate exposure monitoring to determine the employee's exposure levels and medical surveillance, which must be performed by a licensed physician. Now, in general industry, medical surveillance is required for any employees who are or may be exposed to lead above that action level for more than 30 days per year. And the employer must institute a medical surveillance program for those exposed employees. As I said previously, this must be done by or under the supervision of a licensed physician and must be made available to the employee before they are potentially exposed to lead. This monitoring is based on checking the levels of lead in the employee's blood. Employees who are exposed above that action level and or above the PEL will undergo this medical monitoring periodically. Now, the details of the frequency can be found in 1910-1025. Now, in the construction industry, medical surveillance is similar to what is required in general industry, except that initial medical surveillance is required for any employees exposed at or above the action level for any 1 day. Not 30, but for any 1 day. Now, if the employer determined that the employees are exposed at or above the action level for more than 30 days in any 12 consecutive months, then they must institute a medical surveillance program. Here we see an example of the hierarchy of controls. This is a system for controlling risks in the workplace. It's a step-by-step approach to eliminating or reducing risks, and it ranks risk controls from the highest level of protection and reliability through to the lowest and least reliable protection. Eliminating the hazard and risk is the highest level of control in this hierarchy, followed by reducing the risk through substitution, isolation, and engineering controls, and then reducing the risk through administrative controls. Finally, reducing the risk through the use of personal protective equipment, that's the lowest level of control. Now, we're going to be referring back to this hierarchy for all of the health hazards in this presentation. Now, with lead, if you cannot eliminate or find a safer chemical compound that can be substituted, then engineering controls become the top priority. That's where we're going to start in the coming slide. Now, keeping that hierarchy of controls in mind, let's look at some potential abatement methods for lead. Now, engineering controls. Ideally here, you're looking at ventilation and isolating the hazard from the employees. Effective engineering controls will reduce or eliminate lead exposures. You also should look at administrative or work practice controls. If lead levels are still at or above the action level after instituting engineering controls, you might need to initiate other practices. This could include good housekeeping, appropriate personal hygiene practices, periodic inspection and maintenance of process and control equipment. Also, create proper procedures that employees can follow to perform a task, and ensure appropriate supervision to make sure that the proper procedures are being followed. Now, when exposure to lead hazards cannot be engineered completely out of normal operations or maintenance work, and when safe work practices and other forms of administrative controls can't provide sufficient additional protection, you have to look at PPE, or personal protective equipment. This may be appropriate for controlling the hazard. Now, the PPE for lead can include proper respiratory protection and protective work clothing. Once again, these hierarchy of controls are going to be applied to all the hazards we're reviewing today. But the big takeaway is that PPE is your last resort. Try to find some way to eliminate, substitute, or engineer out the hazard first, before applying administrative controls and then finally applying PPE. Next up is hexavalent chromium. So let's take a look at what a hexavalent chromium is. So the metal chromium is an element that exists in several forms, or valence states. The hexavalent form of chromium, or chrome-6, is a stable form that's known to be toxic. Now, hexavalent chromium can exist in many different compounds, and these vary from highly water-soluble to slightly water-soluble to completely water-insoluble. Now, hexavalent chromium compounds have many varied uses in industry and are often used for their anti-corrosive properties in metal coatings, protective paints, dyes, and even pigments. Now, hexavalent chromium can also be formed when performing hot work. This is like welding on stainless steel, melting chromium metal, or heating refractory bricks in kilns. In these situations, the chromium is not originally hexavalent, but the high temperatures cause oxidation that converts that chromium to hexavalent chromium. Now here you can see some of the major industries covered by the 1910-1026 and 1926-1126 standards. There are a large variety of operations where employees can be exposed to hexavalent chromium. So major industrial sources of hexavalent chromium include chromate pigments, which are used in dyes, paints, inks, and even plastics. Chromates added as anti-corrosive agents to paints and primers and other surface coatings. Chrome plating by depositing chromium metal onto an item's surface. Particles released during smelting of ferrochromium ore. Even fumes from welding stainless steel or non-ferrous chromium alloys. And it's even seen as impurities in Portland cement. Now let's take a look at the health effects of hexavalent chromium. The primary health effect of concern is lung cancer. It's caused by airborne exposures to hexavalent chromium. OSHA considers all chrome-6 compounds to be carcinogenic. Now, exposure to chrome-6 can lead to lung cancer in workers who breathe airborne hexavalent chromium. Irritation or damage to the nose, throat, and lungs, can occur if hexavalent chromium is breathed in at high levels. You'll also see irritation or damage to the eyes and skin if hexavalent chromium contacts these organs in high concentrations. Airborne exposures of hexavalent chromium can cause irritation to the nose and throat. Symptoms can include runny nose, sneezing, coughing, itching, and a burning sensation. If this exposure is repeated or prolonged, it can cause sores to develop in the nose and result in nosebleeds. If the damage is severe, the nasal septum, that's that wall separating your nasal passages, will develop a hole in it or a perforation. This is called a chrome hole. Now, exposures can also cause occupational asthma in chromium-sensitized individuals, with symptoms to include wheezing and shortness of breath. Now, some employees can also develop an allergic skin reaction. This is called allergic contact dermatitis. This occurs when handling liquids or solids containing hexavalent chromium. Once an employee becomes allergic, brief skin contact can cause swelling and a red, itchy rash that becomes crusty and thickened with prolonged exposure. Allergic contact dermatitis is long-lasting and more severe with every repeated skin contact. If you have direct skin contact with hexavalent chromium, it can even cause a non-allergic skin irritation. Now, contact between an employee's non-intact skin can also lead to chrome ulcers. These are small crusted skin sores with a rounded border. They heal very slowly and they leave scars. You can see listed here the major provisions of the hexavalent chromium standards. These are provisions commonly included in any OSHA comprehensive health standard. I do want to point out that the provisions for regulated areas and housekeeping apply only to general industry. Now, based on evidence in the rulemaking record, OSHA believes that the variability in hexavalent chromium or Chrome-6 exposures and the unique nature of work involving Chrome-6 exposures in construction make it impractical to effectively establish regulated areas and to perform housekeeping in these sectors. Now, we're going to take a closer look at some of these provisions in the coming slides. So let's talk about exposure limits. OSHA has established legal limits for hexavalent chromium exposure in the workplace. So let's look at the PEL, or the permissible exposure limit. Employers must ensure that no employee is exposed to an airborne concentration of hexavalent chromium in excess of 5 micrograms per cubic meter of air as an 8-hour time-weighted average. Now, this determination must be made without regard to the use of personal protective equipment, such as respiratory protection. What this means is that employers cannot apply the level of protection that the respirator can provide to determine whether an employee is overexposed to hexavalent chromium present in the air. Now, what does this PEL mean for employers? To put it simply, it's the level of employee exposure that you cannot legally exceed for your employees. Second, let's look at the action level. The action level for airborne chromium-6, or hexavalent chromium, is 2.5 micrograms per cubic meter, again calculated as an 8-hour time-weighted average. When exposure levels exceed this threshold, specific requirements come into play, even though employees are not exposed above the PEL. Remember, keeping employee exposure levels as low as possible and not to exceed legal limits is crucial in protecting workers from the toxic effects of hexavalent chromium. OSHA requires that employers determine their employees' exposure to hexavalent chromium. The standard states that exposure monitoring can be done in one of two basic ways. You can choose either one as long as you give a good accounting of the employee's exposure. The first method is by scheduled monitoring. This monitoring must be performed initially and periodically. Now, for exposures that are determined to be at or above the PEL of 5 micrograms per cubic meter, exposure monitoring must be performed at least every 3 months. Now, if there are exposures that are determined to be at or above the action level of 2.5 micrograms per cubic meter, that exposure monitoring must be performed every 6 months. Now, if monitoring shows that exposures are below the action level, then monitoring can be discontinued. Additionally, exposure monitoring must be performed whenever there is a change in work processes or materials that can result in new or additional exposures to hexavalent chromium. Now, the second method is the performance-oriented option, which uses air monitoring data, any historical monitoring data, and any other objective data that can be used to get an accurate reflection of the workplace conditions and the potential exposures to the employees. The data must accurately represent the processes, the types of materials, the control methods, work practices, and environmental conditions. To ensure this method is as accurate as possible, it's recommended that an industrial hygienist or other qualified professional perform this option. So let's look at regulated areas. Remember, the standard only requires regulated areas in general industry, not in construction. Now, these regulated areas are areas that are demarcated by the employer. This is where an employee's exposure to airborne concentrations of hexavalent chromium can be expected to exceed the PEL. To put simply, the purpose of a regulated area is to ensure that employees are aware of the presence of hexavalent chromium at levels above the legal limit. and to limit exposure to as few employees as possible. Now, the standard does not specify how an employer must identify this regulated area, so the employer must choose the means that are appropriate for their workplace. This could be warning signs, ropes, gates, barricades, or other methods as appropriate. Whatever method is selected must effectively warn workers who are not authorized to enter the area. Any workers who do enter the regulated area must use proper protective equipment, including respirators, where needed. Another required provision of the standard is medical surveillance. Medical surveillance serves multiple purposes when considering worker exposure to hexavalent chromium. It allows physicians or other healthcare professionals to determine if an individual can be exposed to hexavalent chromium at their workplace without experiencing adverse health effects. It permits appropriate intervention to be taken when hexavalent chromium-related adverse health effects are identified in an individual. And finally, it determines an employee's fitness to use personal protective equipment, in particular respirators. Now, employers must provide a medical surveillance program for all employees who are exposed or may be exposed to hexavalent chromium at concentrations at or above the action level for 30 or more days per year. Also, for employees who are experiencing signs and symptoms of adverse health effects associated with hexavalent chromium exposures. For those employees who've been exposed to an emergency situation, such as an uncontrolled release of hexavalent chromium. They also need to have this medical surveillance annually and at the termination of employment unless the last examination provided was less than 6 months prior to the date of termination. A licensed physician or similar must perform or supervise all medical examinations and procedures. They must be provided at no cost to employees and at a reasonable time and place. If employees must travel away from the work site, the employer must pay them for the time spent undergoing medical examinations, including travel time. Now let's look at some potential abatements for hexavalent chromium. I do want to mention that because hexavalent chromium is regulated as a carcinogen or cancer-causing agent, employee rotation cannot be used to reduce employee exposures below the PELs. Now let's get started with engineering controls. Now examples include isolation, such as enclosing the source of exposure, and ventilation, such as using a local exhaust system that captures airborne hexavalent chromium near its source. Next, administrative and work practice controls. This involves adjustments in the way a task is performed. Potential controls can include creating proper procedures for employees to follow in order to minimize their exposures, following good housekeeping practices, such as keeping work areas as clean as possible and ensuring employees don't eat, drink, or smoke in areas where there's a potential exposure to hexavalent chromium. Also, providing employees with hygiene facilities, such as washing facilities and changing rooms, as well as training employees to wash their hands and face at the end of a work shift, as well as prior to eating, drinking, or smoking. Also, providing facilities for quick drenching or flushing of the eyes and body are required if employees are exposed to corrosives or otherwise acute acting hexavalent chromium contaminants. An example would be chromic acid. And finally, PPE. If employers are unable to reduce worker exposures to hexavalent chromium at or below the PEL, respirators are required. And if respirators are required, you have to have a respiratory protection program in place and being used. Protective work clothing and equipment must be provided by the employer whenever there is the danger of skin or eye contact with hexavalent chromium. This PPE can include gloves, aprons, foot coverings, goggles, and even coveralls. The PPE provided must be appropriate for the hazard and the tasks that employees are performing. Now let's look at isocyanates. Isocyanates are used to manufacture a lot of different polyurethane products. This includes chemicals, polyurethane foam, insulation materials, furniture, foam mattresses, undercarpet padding, shoes, laminated fabrics, polyurethane rubber, and adhesives, and is created during the thermal degradation of polyurethane products. If you need to find the Pell or permissible exposure limits for isocyanates, you'll have to look into Table Z1 found in the standard under 1910-1200. Now, there is one caveat. You have to look for the specific type of isocyanate you're using. Some examples include methylene bisphenyl isocyanate, also called MDI, methyl isocyanate, and toluene 2,4-diisocyanate, or TDI. Now, it's possible for a chemical to be listed under multiple chemical names. To ensure that you're correctly identifying the type of isocyanate that your employees could be exposed to, compare the CAS or Chemical Abstract Systems number of the chemical to the listing in the Z1 table. Now, the CAS number can be found on a chemical's safety data sheet. You can think of the CAS number like a chemical's social security number. The chemical might have multiple names, but it will only have one CAS number. If you look at the example here on this slide from a Z table, you can see that the CAS number for each of the listed isocyanates is listed there, and each one is different. Now, not all isocyanates are regulated by OSHA. For example, hexamethylene diisocyanate, or HDI. However, there are TLVs, or threshold limit values. These are recommendations by the American Conference of Governmental Industrial Hygienists, or the ACGIH. These are guidelines that can be used to keep worker exposures at a safer level. Let's take a look at the health effects of isocyanates. Now, exposure to isocyanates can include a variety of symptoms. These can include irritation of skin and mucous membranes, chest tightness, and difficulty breathing. Workers can also become sensitized to isocyanates. This can make them subject to severe asthma attacks if they are exposed again. Now, death from severe asthma in some sensitized subjects has been reported. Isocyanates include compounds that are classified as potential human carcinogens and have been shown to cause cancer in animals. Reactions to isocyanates can occur hours after exposure, possibly even after you're at home at night in bed. The employee may not recognize the reaction as associated to the work exposure. Make sure that employees are trained to recognize the symptoms. Once sensitization occurs, the employee needs to be removed from exposure, as even exposures below detectable limits can cause additional reactions. How can isocyanates affect the body? Well, first, a worker is exposed to an isocyanate. Typically, this is through dermal or skin contact or by inhalation. Now, as workers are exposed through their occupational job tasks, sensitization can occur. This means that the worker has now developed an allergy to the isocyanate. As more and more exposures occur, the worker's body will react in more and more dramatic ways until even a small amount of exposure to the isocyanate can cause a serious reaction. Typically, the reactions will include a skin rash, or the worker can develop occupational asthma. These asthma attacks can be very severe if the workers are exposed again after that sensitization occurs. Death from severe asthma in sensitized workers has occurred. Workers potentially exposed to isocyanates who experience persistent or reoccurring eye irritation, nasal congestion, dry or sore throat, cold-like symptoms, cough, shortness of breath, wheezing, and even chest tightness should see a physician knowledgeable in these work-related health problems. It's also important to remember that certain isocyanate compounds have been classified as carcinogens or cancer-causing agents. Medical surveillance serves several purposes when considering worker exposure to isocyanates. It allows physicians or other healthcare professionals to determine if an individual can be exposed to the isocyanate at their workplace without experiencing adverse health effects. It permits appropriate intervention to be taken when isocyanate-related adverse health effects are identified in a worker. And finally, it determines an employee's fitness to use personal protective equipment, in particular respirators. Now, a medical surveillance program should be provided for all employees who are exposed or may be exposed to isocyanates at concentrations at or above the Pell. experience signs and symptoms of adverse health effects associated with isocyanate exposures, or are exposed in an emergency situation, such as any occurrence resulting in an uncontrolled, non-incidental release of isocyanates. Let's look at some potential abatements for isocyanates. First, substitution. If it's possible to do so, look for a less toxic material that can be used instead of isocyanates. If not, engineering controls. Mechanical ventilation can be used. Good example is local exhaust near the source of the exposure. One thing to keep in mind, do make sure that filters are changed or kept clean to ensure its proper functioning. Isolation can also be used. If it's possible, enclose the process or the source of the isocyanate. Administrative controls. Good administrative and work practice controls can complement engineering controls in providing worker protection. Workers must know the best practices when performing a task so that they can minimize their exposure and maximize the effectiveness of the control. For example, workers spraying foam insulation should be trained to position themselves upstream from the direction of spraying and the source of local exhaust ventilation, wherever feasible. Good housekeeping practices also need to be instituted, as well as good personal hygiene. That's washing your hands and face before eating, drinking, or smoking. Regulated areas of work can also be established. Now, while there is not a specific requirement in the standard for regulated areas, employers are encouraged to establish these areas to warn employees where levels of airborne isocyanates can potentially exceed the PEL. And finally, PPE. If employee exposures cannot be maintained below the PEL, respiratory protection will be required. When choosing respirators for protection against isocyanates, employees must consider that there are few air purifying respirator cartridges and canisters available that have end of service life indicators, and there are none available for isocyanates. In addition, many diisocyanates have odor threshold levels that are several times the PEL, which means that by the time you can smell it, you are overexposed. Because of these issues, a full face supplied air respirator is recommended. Protective work clothing could also be required. To protect your skin, the industry recommendation is to wear a full-bodied suit and use chemical-resistant gloves. Our next hazard is beryllium. The element beryllium is a gray metal that is stronger than steel and lighter than aluminum. Its physical properties include great strength to weight ratio, high melting point, excellent thermal stability and conductivity, reflectivity, and transparency to X-rays. All of this makes it an essential material in the aerospace, telecommunications, information technology, defense, medical, and nuclear industries. Now, beryllium is used industrially in three forms: as a pure metal, as beryllium oxide, and most commonly as an alloy with copper, aluminum, magnesium, or nickel. Beryllium oxide, called beryllia, is known for its high heat capacity and is an important component of certain sensitive electronic equipment. Beryllium alloys are classified into two types: high beryllium content, which is up to 30% beryllium, and low beryllium content, which is only 2 to 3% beryllium. Copper beryllium alloy is commonly used to make bushings, bearings, and springs. Fly ash, which is a byproduct of coal-fired power plants, and various abrasive blasting materials such as slags, garnet, silica sand, and crushed glass, can also contain trace amounts of beryllium, typically about 0.1% or less by weight. Here you can see a listing of industries with potential beryllium exposure. As you can see, worker exposures to beryllium can occur in settings as varied as foundry and smelting operations, fabricating, machining, grinding, beryllium oxide ceramics manufacturing, and even dental lab work. Now, OSHA estimates that approximately 62,000 workers are potentially exposed to beryllium in approximately 7,300 establishments in the United States, including approximately 12,000 workers in the construction and shipyard industries. So why is beryllium a hazard? Well, exposure to beryllium, either through inhalation of airborne beryllium or through skin contact with beryllium-containing dust, fumes, mist, or solutions, can cause some serious health effects. Let's look more closely at the health effects in the next slide. Unlike many toxins, there's no threshold below which a worker will not become sensitized to beryllium. The most common health effects associated with overexposure to beryllium include beryllium sensitization, chronic beryllium disease, or CBD, and lung cancer. Beryllium sensitization is the activation of the body's immune system to beryllium. This can result from inhalation or skin exposure to beryllium dust, fume, mists, or solutions. Now, while no clinical symptoms may be associated with this sensitization, a sensitized worker is at risk of developing CBD when inhalation exposure to beryllium has occurred. Now, CBD, or chronic beryllium disease, is a chronic lung disease caused by inhaling airborne beryllium after already becoming sensitized to it. Some common symptoms of CBD are shortness of breath, unexplained coughing, fatigue, weight loss, fever, and night sweats. CBD can result from inhalation exposure to beryllium at levels below the current OSHA PEL, which is 0.2 micrograms per cubic meter. Progression of CBD can vary among individuals. For instance, after initial exposure to beryllium, some workers may quickly develop signs and severe symptoms of CBD. Others may not experience signs and symptoms until months or years after initial exposure. The symptoms can sometimes worsen even after the worker has been removed from exposure. CBD can progress to a chronic obstructive lung disorder, resulting in the loss of quality of life and the potential for decreased life expectancy. And finally, lung cancer. Based on numerous studies in occupational settings, OSHA has determined that occupational exposure to beryllium causes lung cancer in humans. In addition, the International Agency for Research on Cancer, or the IARC, classifies beryllium as a Group 1 carcinogen, which is carcinogenic to humans. And the National Toxicology Program, or NTP, lists beryllium as a known human carcinogen. You can also get something called acute beryllium disease, or ABD. Now, acute beryllium disease is a rapid onset form of chemical pneumonia that results from breathing high airborne concentrations of beryllium. ABD is generally associated with exposure to beryllium levels at or above 100 micrograms per cubic meter and may be fatal in 10% of cases. Now, ABD is extremely rare in the workplace today due to more stringent exposure controls implemented following occupational and environmental standards set in the 1970s. And just as, for your knowledge, people living near plants that use beryllium and families of workers with beryllium exposure have developed CBD. Very low concentrations of beryllium in air can cause sensitization and disease. Now on to the beryllium exposure limits. Now the PEL for beryllium is 0.2 micrograms per cubic meter, calculated as an 8-hour time-weighted average. OSHA established this PEL because the agency determined that occupational exposure to beryllium at the previous PELs resulted in significant risk of developing CBD or dying from CBD or lung cancer, and that compliance with a 0.2 micrograms per cubic meter PEL would substantially reduce that risk. Beryllium also has an action level of 0.1 microgram per cubic meter, calculated as an 8-hour time-weighted average. The standard also sets a 15-minute or short-term exposure limit of 2.0 micrograms per cubic meter over a 15-minute sampling duration. Next, let's look at monitoring methods for beryllium. Now, these methods are very similar to what's required for hexavalent chromium, so it may feel familiar. The first method is the performance option. Now, the employer must assess each employee's exposure data for beryllium to include 8-hour time-weighted average data and the STEL, as well as any air monitoring data and other objective data that is relevant and provides sufficient information to accurately characterize that employee's airborne exposure to beryllium. Now, the second method is the scheduled monitoring option. Now, here the employer must perform initial monitoring for those 8-hour time-weighted averages and the STEL. Now, if the initial monitoring indicates that exposures are below the action level or less than or equal to the short-term exposure level, monitoring can be discontinued. If it's found to be at or above the action level or less than or equal to the STEL, monitoring must be done every 6 months. If it's above the PEL, monitoring must be done every 3 months. Now, airborne exposures must also be reassessed whenever there is a change in the production, process, or controls. Medical surveillance under beryllium standards requires employers to offer medical surveillance to workers within 30 days of determining that that worker meets at least one of these following conditions: that they are reasonably expected to be exposed above the action level of 0.1 microgram per cubic meter for 30 days in a year, show signs or symptoms of CBD, that they were exposed to beryllium during an emergency, or have received a recommendation for continued medical surveillance from a physician or other licensed healthcare professional from their most recent exam. Now, employees can opt out of the medical surveillance program if they choose to do so. Now, the medical examination must include the medical and work history of the employee with an emphasis on past and present airborne exposures or dermal contact with beryllium, their smoking history, and any history of respiratory system dysfunction. It must also include a physical examination with emphasis on the respiratory system, a physical examination for any skin rashes, a pulmonary function test, and a beryllium lymphocyte proliferation test, or a BLPT. This is a test for measuring the body's immune response to beryllium, or any other equivalent test that the doctor deems necessary. Now, in the beryllium standard, OSHA requires that the employer ensure that the employee receives a written medical opinion from that licensed physician within 30 days of the medical examination. This written opinion must include the results of the medical examination, any medical conditions related to airborne exposure that might require further evaluation or treatment. The written opinion must also include any recommendations on the employee's use of PPE or respirators, any limitations on the employee's airborne beryllium exposure, and any recommendations for referral to a CBD diagnostic center, continued medical surveillance, or medical removal. Let's do a quick recap. Workers are primarily exposed to beryllium by breathing in dusts, fumes, or mists containing beryllium. Beryllium compounds can also get on the skin, contaminate clothing or food, and be ingested. The most effective way to prevent exposure to a hazardous metal such as beryllium is through elimination or substitution with a viable, less toxic alternative. If that's just not possible, then we move on to engineering controls. Now, for beryllium, this would include isolating the source of the exposure and using local exhaust ventilation to remove the hazardous substance before it ever enters the worker's environment. Administrative and work practice controls, these should include proper cleaning and housekeeping methods, including the use of HEPA vacuuming and wet mopping instead of dry sweeping. The employer must ensure that employees remove all beryllium-contaminated PPE and clothing at the end of the shift, when all tasks are completed, or when visibly contaminated with beryllium. The employees must have a place to change and ensure that their street clothes are not contaminated with beryllium. To take contaminated items home is to expose the employees and their families to the hazard. Of note, job rotation cannot be used to achieve compliance with the PELs, as beryllium is a cancer-causing agent. And then PPE. This includes wearing the proper respiratory protection if there is a possibility of inhalation exposure, and protective clothing when there is a reasonable expectation of dermal contact. 1910-1024 states that the employer must provide at no cost to the employee a powered air purifying respirator or PAPR instead of a negative pressure respirator when respiratory protection is required by this standard. Our next hazard is silica. The OSHA silica standards apply to crystalline silica only. Amorphous silica exposures are covered under mineral dusts in the standard. Now, silica dust is released as a result of crushing and grinding substances like concrete, brick, natural stone, all those granite countertops that we have in our kitchen. When somebody made those, they were making silica dust. Now, the smallest of these particles that are generated are called respirable crystalline silica. These are very, very small. They're about 100 times smaller than a grain of sand that you can find on the beach. Now, when these very fine respirable crystalline silica particles are breathed in, they travel deep into your lungs, into the smallest parts called the alveoli. This is where gas exchange occurs, and where these particles can become trapped and cause disease. Breathing in very small or respirable crystalline silica particles can cause multiple diseases, including silicosis, an incurable lung disease that leads to disability and death. When the silica dust enters the lungs, it causes the formation of scar tissue, which makes it difficult for the lungs to take in oxygen. Now, like I said, there's no cure for silicosis, but it can be prevented. Early symptoms include becoming short of breath, tiring easily, and developing a cough. These symptoms will become more severe the longer an employee works around the hazard and breathes in the dust. Silicosis typically occurs after 15 to 20 years of occupational exposure to respirable crystalline silica. Symptoms may or may not be obvious. Therefore, workers need to have a chest x-ray to determine if there's lung damage. As the disease progresses, the workers may experience, again, shortness of breath upon exercising. In the later stages, workers may experience fatigue, extreme shortness of breath, chest pain, or even respiratory failure. Because silicosis affects the immune system, exposure to silica increases the risk of lung infections, such as tuberculosis. In addition, smoking causes lung damage and adds to the damage caused by breathing in the silica dust. Silica exposure can cause more than just silicosis. At least 1.7 million U.S. workers are exposed to respirable crystalline silica in a variety of industries and occupations, from construction to sandblasting to mining. Unless a doctor knows that you work around silica, the disease can go undiagnosed. Symptoms can come on gradually and resemble other problems, such as a smoker's cough or ordinary fatigue. Workers who are exposed to silica dust may want to consult a specialist in this area. Exposed workers should have an X-ray every 2 or 3 years and a lung function test once a year. Medical exams are helpful but cannot be relied upon as a primary protective measure. Preventative measures are essential because the disease is often well advanced before detection. Breathing in silica can increase employees' chances of developing lung diseases, to include silicosis, but also lung cancer, chronic obstructive pulmonary disease, or COPD. It also increases their chances of developing kidney and autoimmune diseases. The higher the levels of silica that employees are exposed to, and the longer that they're exposed to it, the greater the chances of developing these diseases. Silicosis and COPD are lung diseases that are permanent and incurable, and are often deadly or disabling. Less than 16% of people diagnosed with lung cancer live longer than 5 years. Kidney diseases can cause problems like high blood pressure or even end-stage renal disease, which often requires dialysis or a kidney transplant. Autoimmune diseases occur when antibodies that protect the body from diseases attack the body itself. Now, occupational exposure to respirable crystalline silica is associated with the development of silicosis, lung cancer, pulmonary tuberculosis, and other airway diseases. But like I just mentioned, you can also get the development of autoimmune disorders, chronic renal disease, and other adverse health effects. With silica, the hazard exists when this material is released as a dust, typically as a result of crushing and grinding. Breathing this free silica dust either in large quantities or over a long period of time can cause lung diseases like silicosis that we looked at earlier. The small dust particles remain in your lungs and they scar your lung tissue. If the employer suspects that silica is a hazard at the workplace, even if it's not known for sure, they are still required by OSHA to communicate this potential hazard to all employees, and training is required. Here you can see a list of industries with known silica exposure. Now these industries are quite varied and range from concrete mixing, the electronics industry, jackhammer operations, to even setting, laying, and repairing railroad track. Now with silica, the exposure limits are for the action level 25 micrograms per cubic meter over an 8-hour time-weighted average. If you hit the action level, you are required to have a written exposure control plan. Now the PEL is 50 micrograms per cubic meter, again as an 8-hour time-weighted average. If this PEL is reached or exceeded, engineering controls must be put into place, and respiratory protection will be required. Medical monitoring or surveillance of workers can help identify health effects related to respirable crystalline silica exposure. Periodic medical monitoring helps to detect silicosis at early stages so workers can avoid further exposure and potentially limit the progression of disease. Listed in the slide here are the legal requirements per the standard. It must be provided at no cost to the employee and at a reasonable time and place. This is typically work hours. For general industry, medical surveillance is required if you have employees exposed at or above 25 micrograms per cubic meter for 30 or more days for any 12 consecutive months. For construction, it's a little different. It's for when any employee is required to wear a respirator 30 or more days for any 12 consecutive months. In the construction industry, there are specific control methods that are listed. This is Table 1. It lists 18 very specific tasks, and it identifies the specific engineering controls that can be used. If all of the requirements of the table are followed, the employer is not required to conduct silica monitoring. Here is an example from that Table 1. If you can see here, it says equipment and task. This is for handheld power saws, any blade diameter. Then you go to engineering and work practice control methods, and here you see it says use the saw equipped with integrated water delivery systems that continuously feed water to the blade, and follow all manufacturer's instructions. Now, it gives you two choices. You can use it outdoors or use indoors or an enclosed area. That's going to affect the required respiratory protection. So we go to the next column, and then again you have two choices. It's for less than or equal to a 4-hour shift or greater than a 4-hour shift. So we start to the one to the left. If it's 4 or less hours in the shift, if you're working outdoors and you have that integrated water delivery system, you're not required to use any respiratory protection. However, if you move indoors or in an enclosed area, you have to use respiratory protection with an assigned protection factor of 10. Now, if you look in the next column where you got greater than 4 hours, it doesn't matter. It says if you're outdoors or you're indoors, you have to use respiratory protection with an APF of 10. So let's look at some abatements for silica. Let's look at engineering controls. Mechanical ventilation. The most effective control of airborne concentrations of silica is at the source of the contamination. Enclose that operation or use local exhaust ventilation. If you're going to enclose a process or operation, a slight vacuum should be used to create negative pressure. So that leakage will result in the flow of external air into the enclosure and minimize contamination of the workplace. This can be accomplished with a well-designed local exhaust ventilation system that physically encloses the process as much as possible with sufficient capture velocity to keep the contaminant from entering the work atmosphere. Then administrative controls. As most of the things we've looked at today, you need good housekeeping practices. The development of good work procedures so that the employees are following safe practices, safe work practices. Also, work clothes should be vacuumed before removal. General housekeeping duties should be intensified so that there is no dust accumulation on machinery, beams, corners, or any other surfaces. Such accumulations often contain respirable particles which can become airborne when disturbed. Dustless methods of cleaning, such as vacuuming or wetting down, should be used. Dry sweeping or blowing with compressed air should be avoided. And PPE, respiratory protection. To protect your lungs, wear a full-face supplied air respirator. To help you see and to keep your mask clean, it's recommended to use a peel-off shield on this full-face respirator. In summary, we've discussed the Health Hazards SCP program, specifically looking at hexavalent chromium, or Chrome 6, isocyanates, lead, beryllium, and silica. Now for each of these we looked at how employees can be exposed, the various health effects of each, as well as potential abatement methods. Thank you for attending today's session. If you have any questions, please feel free to call our 1-800-NC Labor telephone line or check out our website, www.labor.nc.gov.